Whether we are trying to understand the nature of the very small or the very large, optical instruments provide us with versatile and powerful devices to help us in this quest. Optical instruments are devices that process light waves, either to enhance an image for viewing or to analyze its characteristics and properties. Optical instruments are designed using reflecting and refracting properties of mirrors, lenses, and prisms. Here we are studying a few optical devices starting with the eye. Yes, the human eye is one of the most important optical devices endowed upon us by nature. Let's first understand the parts of the eye which play a part in vision. Number 1, the cornea. The cornea is the front surface of the eye. It is transparent. 2, the pupil. It is the central hole in the iris whose size can change under the control of muscles. Next we have the lens of the eye, which is transparent and can change its thickness with the same muscles. Then we have the retina. It is a film of nerve fibers covering the curved back surface of the eye. The retina is composed of rods and cones, which are specialized cells sensing light intensity and color respectively. How does the eye work? Light enters into the eyes through the cornea and passes through the pupil. The lens of the eye then focuses an image of the object on the retina. The rods and cones in the retina are sensing the light intensity and the light color respectively and transmitting electrical signals through nerves into the brain. The brain finally processes the information and provides us with what we understand as an image. Now, the shape or the curvature and hence the focal length of the lens can be modified by the ciliary muscles. For example, when the muscle is relaxed, the focal length of the eye is about 2.5 centimeters and objects at infinity are in very sharp focus on the retina. When the object is brought closer to the eye, in order to maintain the same image lens distance, that is 2.5 centimeters, the focal length of the eye will change, or the lens in particular will change, becoming shorter through the action of these ciliary muscles. And this property of the eye, the ability to adapt the focal length to the position of the object, is known as accommodation. The near point or the least distance of distinct vision happens when the object is too close to the eye and the lens cannot curve enough to focus the image onto the retina, and so the image gets blurred. The closest distance for which the lens can focus light on the retina accurately is called the least distance of distinct vision, or the near point of vision. The standard value for normal vision near point is taken as 25 centimeters, and often this point is given by the symbol capital D. Now, we will discuss some of the possible defects that the eye can suffer from. We will start with something called presbyopia. With age, the effectiveness of the ciliary muscles decreases and the lens also begins to lose flexibility. Thus, if an elderly person tries to read a book at about 25 centimeters from the eye, the image appears blurred. This condition, this defect of the eye is called presbyopia. It is corrected by the use of a converging lens for reading. Next, we deal with myopia or nearsightedness. When light from distant objects arriving at the eye lens gets focused at a point in front of the retina, it means that the lens of the eye is producing too much convergence and as a result, the vision is blurred. This type of defect is called nearsightedness or myopia. To compensate for this, we interpose a concave lens between the eye and the object with the diverging effect desired to get the image focused on the retina. Hypermetropia or farsightedness or simply hyperopia is a defect that happens when the eye lens is focusing the incoming light at a point imaginary or behind the retina. In this case, we need a convergent lens in order to compensate for this defect in vision. This is also called farsightedness or simply hyperopia. Next, we come to something called astigmatism. In astigmatism, what happens is that the cornea is not perfectly hemispherical in shape. As a result, the lines in one direction will seem very well focused, but lines in the perpendicular direction may appear distorted. Astigmatism can be corrected using a cylindrical lens of the desired radius of curvature with an appropriately directed axis. Now we come to optical instruments, starting with the microscope. The microscope is an optical instrument consisting of one or a combination of lenses for magnifying and inspecting objects which are too small to be seen by the naked eye. A simple microscope or magnifier is simply a convex lens, a converging lens with a small focal length. The object is placed between the lens and the focal point. The eye is positioned close to the lens on the other side. A magnified, erect and virtual image is viewed on the same side as the object at a distance at which it can be viewed comfortably, which is approximately 25 centimeters or more. The linear magnification of the final image formed at the least distance of distinct vision D is derived from the lens formula, and it is given as D upon U is equal to capital M. Next we come to the compound microscope. A simple microscope has a very limited maximum magnification. If we want to achieve larger magnifications, we will use the combination of two convex lenses called the objective lens and the eyepiece, separated by a distance. So one is compounding the effect of the other. Now, the focal length of the objective lens in this case will be less than the focal length of the eyepiece. The objective lens will form a real, inverted and magnified image of the object. Now, the magnification due to the object is given as M is equal to H dash upon H. That is the size of the image divided by the size of the object. If we use the familiar lens formulae, we can calculate this value as M is equal to 1 upon D upon Fe. The image from the first, that is the objective lens, acts as the object for the second lens. So the eyepiece is functioning essentially like a simple microscope or magnifier. Next we come to the telescope. The telescope is also made up of a series of convex lenses. But here, the objective lens has a larger focal length and aperture compared to the eyepiece. Light from a distant object enters the objective and a real image is formed in the tube at its second focal point. The eyepiece magnifies this image, producing the final inverted image that is observed by the observer. The main considerations for astronomical telescopes are the light gathering power of the telescope and 2, the resolving power of the telescope. Now, the light gathering power depends on the area of the objective lens. The larger the diameter of the lens, the fainter the objects that we can see. This is why astronomical telescopes often have very large objective mirrors or objective lenses. The resolving power is the ability to observe two objects in the same direction distinctly as two separate objects. This also depends on the diameter of the objective lens. So, a large diameter of objective lens is desirable for any optical telescope. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.